Denial of service, DOS. This category is very broad, but fundamentally consists of attacks where users can render a contract inoperable for a period of time, or in some cases permanently. This can trap Ether in these contracts forever, as was the case in real-world example Parity multi-sig wallet, second hack. The vulnerability. There are various ways a contract can become inoperable. Here, we highlight just a few less obvious solidity coding patterns that can lead to DOS vulnerabilities. 1. Looping through externally manipulated mappings or arrays. This pattern typically appears when an owner wishes to distribute tokens to investors with a distribute-like function, as in this contract. Contract distribute tokens, open brace, address public owner, address array investors, uint array investor tokens. Function invest with no parameter, external payable, open brace, investors.push with one argument, message.sender. Investor tokens.push with one argument, message.value times 5. Close brace. Function distribute with zero parameter, public, open brace. Require message.sender equals owner. For I in the range 0 to investors.length. Open brace. Transfer token with two arguments, the ith investor and the ith investor tokens. Close brace, close brace, close brace. Notice that the loop in this contract runs over an array that can be artificially inflated. An attacker can create many user accounts, making the investor array large. In principle, this can be done such that the guess required to execute the for loop exceeds the block guess limit, essentially making the distributes function inoperable. 2. Owner operations. Another common pattern is where owners have specific privileges in contracts and must perform some task in order for the contract to proceed to the next state. One example would be an initial coin offering (ICO) contract that requires the owner to finalize the contract, which then allows tokens to be transferable. For example, Boolean public is finalized equals false. Address public owner. Function finalized with no parameter, public, open brace, require message.sender equals owner, is finalized equals true, close brace. Function transfer with two parameters, address underscore to, uint underscore value, returns Boolean, open brace, require is finalized, super.transfer with two arguments, underscore to and underscore value, close brace. In such cases, if the privileged user loses their private keys or become inactive, the entire token contract becomes inoperable. In this case, if the owner cannot call finalize, no tokens can be transferred. The entire operation of the token ecosystem hinges on a single address. 3. Progressing state based on external calls. Contracts are sometimes written such that progressing to a new state requires sending Ether to an address, or waiting for some input from an external source. These patterns can lead to DOS attacks when the external call fails or is prevented for external reasons. In the example of sending Ether, a user can create a contract that does not accept Ether. If a contract requires Ether to be withdrawn in order to progress to a new state, consider a time-locking contract that requires all Ether to be withdrawn before being usable again. The contract will never achieve the new state, as Ether can never be sent to the user's contract that does not accept Ether. Preventative techniques. In the first example, contracts should not loop through data structures that can be artificially manipulated by external users. A withdrawal pattern is recommended, whereby each of the investors call a withdraw function to claim tokens independently. In the second example, a privileged user was required to change the state of the contract. In such examples, a fail-safe can be used in the event that the owner becomes incapacitated. One solution is to make the owner a multi-sig contract. Another solution is to use a time lock. In the example given, the require on line 5 could include a time-based mechanism such as message.sender equals owner or now is greater than unlock time. That allows any user to finalize after a period of time specified by unlock time. This kind of mitigation technique can be used in the third example also. If external calls are required to progress to a new state, account for their possible failure, and potentially add a time-based state progression in the event that the desired call never comes. Note: of course, there are centralized alternatives to these suggestions. One can add a maintenance user who can come along and fix problems with DOS-based attack vectors if need be. Typically, these kinds of contracts have trust issues because of the power of such an entity. Real-world examples: governmental. Governmental was an old Ponzi scheme that accumulated quite a large amount of Ether, 1100 Ether at one point. Unfortunately, it was susceptible to the DOS vulnerabilities mentioned in this section. A Reddit post by Etheric describes how the contract required the deletion of a large mapping in order to withdraw the Ether. The deletion of this mapping had a gas cost that exceeded the block gas limit at the time, and thus it was not possible to withdraw the 1100 Ether. The contract address is 0xf4 ... and you can see from transaction 0x0d80 ... that the 1100 Ether were finally obtained with a transaction that used 2.5 M gas. In other words, when the block gas limit had risen enough to allow such a transaction. Block timestamp manipulation. Block timestamps have historically been used for a variety of applications, such as entropy for random numbers, blocking funds for periods of time, and various state-changing conditional statements that are time-dependent. Miners have the ability to adjust timestamps slightly, which can prove to be dangerous if block timestamps are used incorrectly in smart contracts. Useful references for this include the Solidity docs and Joris Bonge's Ethereum Stack Exchange question on the topic. The vulnerability. Block.timestamp and its alias, now, can be manipulated by miners if they have some incentive to do so. Let's construct a simple game, shown in roulette.sol, that would be vulnerable to miner exploitation. Contract roulette, open brace, uint public past block time. Constructor with no parameters, external payable, open brace, close brace. Function with no parameter, external payable, open brace. Require message.value equal 10 Ether. Require now not equal to past block time. Code comment. Only one transaction per block. Past block time equals now. If now modulo 15 equals 0, open brace. Code comment. Winner. Message.transfer of this.balance. Close brace, close brace, close brace. This contract behaves like a simple lottery. One transaction per block can bet 10 Ether for a chance to win the balance of the contract. The assumption here is that block.timestamp's last two digits are uniformly distributed. If that were the case, there would be a 1 in 15 chance of winning this lottery. However, as we know, miners can adjust the timestamp should they need to. In this particular case, if enough Ether pools in the contract, a miner who solves a block is incentivized to choose a timestamp such that block.timestamp or now modulo 15 is 0. In doing so, they may win the Ether locked in this contract along with the block reward. As there is only one person allowed to bet per block, this is also vulnerable to front-running attacks. In practice, block timestamps are monotonically increasing, and so miners cannot choose arbitrary block timestamps. They must be later than their predecessors. They are also limited to setting block times not too far in the future, as these blocks will likely be rejected by the network. because nodes will not validate blocks whose timestamps are in the future. Preventative techniques. Block timestamps should not be used for entropy or generating random numbers. In other words, they should not be the deciding factor, either directly or through some derivation, for winning a game or changing an important state. Time-sensitive logic is sometimes required, for example, for unlocking contracts, time locking, completing an ICO after a few weeks, or enforcing expiry dates. It is sometimes recommended to use block.number and an average block time to estimate times, with a 10-second block time. 1 week equates to approximately 60,480 blocks. Thus, specifying a block number at which to change a contract state can be more secure, as miners are unable to easily manipulate the block number. The BAT ICO contract employ this strategy. This can be unnecessary if contracts aren't particularly concerned with minor manipulations of the block timestamp, but it is something to be aware of when developing contracts. Real-world example: governmental. Governmental, the old Ponzi scheme mentioned above, was also vulnerable to a timestamp-based attack. The contract paid out to the winner who was the last player to join a round. Thus, a miner who was a player could adjust the timestamp to a future time to make it look like a minute had elapsed, to make it appear that they were the last player to join for over a minute, even though this was not true in reality. More detail on this can be found in the History of Ethereum Security Vulnerabilities, Hacks and Their Fixes post by Tanya Barinovska.